So for this reaction between chlorine dioxide and hydroxide to generate chlorate, chlorite, and water, we have the following rate data. We run the reaction under 3 different experiments where we vary the concentration of chlorine dioxide and hydroxide in an effort to determine the rate law for this reaction. And in class we talked about how if I double the concentration and the rate doubles, that's a first order relationship, and if I double the concentration and rate quadruples, that's a second order relationship. But we also have a way to calculate that. And the way to calculate that rate order is using this equation. Take the concentration that's higher divided by the lower concentration raised to the value x, and that should equal the rate of the higher reaction divided by the rate of the lower reaction. Where x is what we're looking for. X is what is the reaction order with respect to that component in the reaction. Order of reaction with respect to the reagent. So for the first calculation, we want to compare entries 1 and 2. I want to use entries 1 and 2 because the concentration of chlorine dioxide changes and the concentration of hydroxide stays the same. I only want one variable at a time. So to find the order of the reaction with respect to chlorine dioxide, I'm going to take the higher concentration, so 0.06, divided by the lower concentration, 0.02. That's raised to the value of x. X is what I'm trying to find. What is the order of the reaction with respect to chlorine dioxide? Then I want to divide by the rate of the higher concentration reaction, so the higher rate, 0.0248, divided by 0.00276. And I get 3 to the x equals 9. So we're trying to figure out what is x. Well, 3 squared equals 9. So x must be 2. And so with respect to chlorine dioxide, right, the reaction is second order. I'm going to do the same calculation for the hydroxide, except for now with hydroxide, I want to use experiment 2 and 3 to determine the rate of the order of the reaction. Because with experiment 2 and 3, I change the concentration of hydroxide, and now the concentration of chlorine dioxide stays constant. I only want one variable at a time when I'm doing these calculations. So for hydroxide, I'll do the same calculation where I'm going to take the larger concentration, 0.09, divided by 0.03, raised to the value of x equals my larger rate is 0.00828 divided by 0.00276. So for that calculation, I get 3x equals 3. So in this case, what must x be, right? X must equal 1. So with respect to hydroxide, it's first order. So now to put those both together in the rate law of the reaction, I would say the rate law for this reaction is rate equals the rate constant times the concentration of chlorine dioxide squared times the concentration of hydroxide to the first power. It's second order with respect to chlorine dioxide, and it's first order with respect to hydroxide. Overall, it's a third order reaction. For the second calculation, calculate the rate constant with proper units. Well, for that, all we need to do is take the rate law that we just developed and basically just pick one of these experiments and plug in the values that we know. So I'm just going to say I'm going to take the first experiment and the data from the first experiment. So for that first experiment, my rate of the reaction is 0.0248 molar per second. That's going to equal my rate constant, that's what I'm trying to find, times the concentration of chlorine dioxide in the first experiment, which is 0.06, squared, times the concentration of hydroxide, 0.03 molar to the first. So if I square the concentration of chlorine dioxide and multiply it by the concentration of hydroxide, I get 0.0248 molar per second equals K times the concentration times the product of that, which is 0.000108 molarity cubed. Molarity cubed because I squared this concentration and then I multiplied it by this concentration. So you add those exponents together. So now I'm going to divide both sides by my concentration cubed. So 0.00108. And I'm going to divide this side as well by 0.000108. And when I divide across, right, one of those cancels out, one of these cancels out, and that leaves me with molarity squared. When I bring that above, that's going to give me a value of K of approximately 230 molarity to the -2 seconds to the -1. Right, the rate constant for a third order reaction, the units of that rate constant should always be molarity to the -2 times seconds to the -1. And again, this shortcut, we didn't go over this in class, but this is a good way, an easy way of helping to figure out the rate order of a reaction. The important thing being you need to pick 2 experiments when only one concentration is changing, and you need to use the rate data from those experiments.